Let's plunge into a world which the human eye cannot normally see. Rugged reefs and filigree crystals. But it isn't a coral reef. It is the result of costly destruction which causes damage to the value of over 80 billion euros every year in Germany alone. Rust. Two scientists from Düsseldorf have set themselves the task of preventing such damage through corrosion. Their vision is that the material should repair itself. Almost by magic.
We were interested to find out how we could develop a coating which prevents this corrosion effect, which doesn't prevent it, but which slows it down, which recognizes defects and repairs the defects itself, with the result that you have a coating that keeps on repairing itself. That is what fascinated us, and so we have been working very successfully in this field.
At the Max Planck Institute for Eisenforschung, an international team is developing a completely novel process. Under Martin Stratmann and Michael Rohweder, they are making use of the electrochemical processes which occur when metal corrodes. The reaction starts when iron comes into contact with oxygen and water. Here, the red girls, oxygen, are stealing the balls, that is, the electrons, from the iron metal boys. Together with the water, they now form hydroxides. Without their electron, the iron boys leave the hard metal. First, they form iron 2 hydroxide with 2 of the ball-playing hydroxide groups. Later, with more oxygen, it will form reddish-brown iron 3 oxide hydroxide. A process which has existed for many years provides the basis for the new corrosion protection. Galvanized surfaces. A fairly thick layer can protect the iron beneath.
Here we can see a picture of the zinc layer viewed through an electron microscope. The zinc crystals on the surface are clearly visible. They produce the matte sheen we have here. And if we have a scratch in the zinc layer, the zinc will disintegrate. It sacrifices itself to protect the steel. That is the first function. The second function is that the corrosion products condense on the steel, as we can see clearly in these zinc oxide platelets, which have condensed on the steel and formed a second skin, in principle thus providing a first protective mechanism. And that is the basis for the corrosion protection using zinc.
Zinc protection occurs because zinc, a base metal, protects the nobler metal iron from oxygen attack. Zinc oxidizes more easily than iron. It sacrifices itself for the iron and reacts with the oxygen to form zinc oxide. This forms a protective layer against further attack on the surface of the metal, because zinc oxide takes up more space than pure zinc and can thus even gradually fill in a crack. So a zinc layer can also repair itself.
But when the zinc is disintegrated, then it's finished. It can't be repaired again, and the corrosion of the iron will begin. So that's why we use thick layers of zinc. However, at the same time, these thick layers of zinc are very difficult to weld. Vapors form in the welding seam, which are very hard to control. And so it is essential that these galvanized sheets of metal should be properly welded.
The scientists are looking for a possibility of making the zinc layer just half as thick, and then protecting it with a special varnish. But here we have a problem. No varnish can provide perfect protection against corrosion in the long term. The scientists investigate various candidates. In order to test the corrosion protection, they develop a familiar instrument further, the Kelvin probe. It shows whether a metal is being corroded, even if it is covered by a fully intact layer of varnish.
So we carried out a simple experiment. We took an iron surface, sprinkled some common salt on it, and then painted it with varnish. We let the varnish dry out overnight, and the next morning we examined it with the Kelvin probe, and, lo and behold, you could see the corrosion effect. And you could also see how it was spreading. For us, that was a real winner, and so we opened a bottle of sparkling wine to celebrate. I must admit that it was a moment that as a scientist you will never forget.
The Kelvin probe measures the electrical tension to find out how much effort is necessary to release electrons from a surface. The remarkable thing is that the process functions even through a layer of varnish. If the varnish and metal surface are firmly bonded together, that is not so easy. The probe measures high tension. But what happens when the layer of varnish and even the zinc beneath it get a deep scratch? Then the steel is no longer protected from water and oxygen. So now the corrosion can eat into the metal, even underneath the varnish. The Düsseldorf scientists were able to observe the destructive work with the Kelvin probe. The metal is coated with ordinary varnish. As soon as the varnish is damaged, oxygen and water penetrate through to the metal and corrosion begins. The varnish peels off the metal. The tension sinks because the Kelvin probe can more easily draw the electrons away from the surface of this varnish, which only appears to still be intact.
In order to increase the lifespan considerably, here we decided that we needed to create a new layer of varnish on the defect, one which repairs itself like human skin. We want to achieve this by actively releasing components from the zinc layer, which would then react with components which we actively release from the layer of varnish. In this way, we want to bring about the repair, and we are quite successful here.
Until now, it was considered difficult to bring about the spontaneous repair of plastic varnishes. Michael Rohwerde is testing the new process. At the beginning, the tension is uniformly high. But the brine results in a sudden drop round the scratch, a sign that corrosion is starting. But then the tension gradually starts to rise again and shows that the corrosion is slowing down. Within a day, the scratch has even been repaired. The way that the varnish repairs itself is partly due to these little spheres. Each one is only about 500 nanometers in size.
These are the so-called raspberry particles, which contain one of the components which we need for the self-repair, and so we incorporate them into the layer of varnish.
The scientists supply the varnish with the raspberry capsules containing the monomers to the metal. As soon as the varnish and the zinc layer beneath are damaged and corrosion begins, the electrons which separate out of the zinc layer produce chemical changes in the casings surrounding the monomer capsules in the varnish. The capsules become permeable. The monomers are released, but they will not be able to combine to form a new varnish on their own. It will take a so-called catalyst to enable the monomers to form a polymer varnish, and that is directly beneath the layer of varnish hidden in the layer of zinc.
Here you can see the black dots in the zinc layer. If you zoom in here, you can see quite clearly that here we have the zinc crystals. They are little capsules here. And now they are clearly visible and contain the second component of our invention, which we need to form a new layer of varnish over a defect.
The casein around these depot capsules consists of silicon dioxide. When the corrosion begins, they become permeable and release their contents. Now the catalyst comes into contact with the free monomers, which combine to form polymers, a new varnish.
And that is the real trick. Something is released, and at the very moment when it is repaired, the electrical signals are changed again. The process comes to a halt, which means that the remaining depots are still basically intact and are thus retained. That's the expertise we have here at the Institute, which we want to continue.
So far, the self-repair only works for small cracks, but the Max Planck scientists are continuing to work on improvements, so that corrosion soon really will belong on the scrap heap.